Alrighty, our last section deals with what's called electrolysis. This is section 20.9. Notice that we actually did skip a couple of sections. One of them is about batteries. Batteries are not covered on the AP exam. This one does deal with electricity, um, and this is unfortunately a very important section. Okay, so today we're going to calculate time, current, amount of substance produced by electrolysis. We're going to calculate the work performed by a voltaic cell. Okay, we know that voltaic cells are based on spontaneous oxidation reduction reactions where E is equal to a positive value, delta G is equal to a negative value. Okay, but some redox reactions are not spontaneous, are not naturally spontaneous. But it is possible to use electrical energy to cause those non-spontaneous redox reactions to occur. Okay, when you have a non-spontaneous redox reaction, you can use an electrolytic cell. And those in an electrolytic cell, electrolysis occurs. Okay, now how do you know whether it's a voltaic cell or an electrolytic cell? They'll usually tell you electricity is passed through a substance, or it will actually use the words, it'll call it an electrolysis reaction, or it'll say, instead of saying a voltaic cell, it'll use the words in an electrolytic cell, blah, blah, blah. For example, electricity can be used to decompose sodium chloride into its component elements, sodium and chlorine. That is a form of an electrolytic reaction. Okay, now an electrolytic cell is very similar to a voltaic cell. Obviously, the main difference being that it's not spontaneous, that it uses electricity. But it does use two electrodes. It does use a solution or a melted salt. Reduction still occurs at the cathode. Oxidation still occurs at the anode. Okay, now if we use NaCl as an example, the Na plus ions pick up electrons and are reduced to sodium at the cathode. And then as the sodium ions near the cathode are depleted, more sodium ions come in. Chlorine, the same thing, where they are oxidized. So sodium goes from +1 to 0, chlorine goes from -1 to 0. So this is reduction, this is our oxidation here. Okay, looks very similar to an electrolytic cell. Again, for that to occur though, you have to have that source of electricity to cause it to occur. Okay, for any half reaction, the amount of a substance that's reduced or oxidized in an electrolytic cell is proportional to the number of electrons passed into the cell. And we'll talk about what that means here in just a second. The quantity of that charge passing through the circuit is generally measured in what's called coulombs. Remember when we talked earlier that a volt is equal to a joule coulomb, and then we use that Faraday's constant. It had coulombs, but we wrote it as joules over volts. Now we're back to coulombs again. Coulomb is equal to 1 mole of electrons and that 1 mole of electrons have 96,500 coulombs. That's a conversion we're going to have to use. Just like 1 mole has 6.02 times 10 to the 23 particles, 1 mole of electrons has 96,500 coulombs, which we know is equal to 1 Faraday. Okay, a coulomb is the quantity of charge passing a point in a circuit in 1 second when the current is 1 amp. A lot of different terms here. Let's just get it. We'll get it all out here, then we'll work a problem together. So therefore, the number of coulombs passing through a cell can be obtained by multiplying the amps times the seconds. A coulomb is an amp second. So here we can kind of see this whole thing all together. When you have the current in amps and they give you the time, which again must be in seconds, you multiply those together to get coulombs. Then you use the coulombs and you use that 1 mole of electrons equals 96,500 coulombs to get moles of electrons. You use that to get the moles of the substance, and then you use the molar mass to go from moles to grams. Okay, so here's an example. They want us to calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the electrical current is 10 amps. So we've got our amps, we've got our time. We need to take our amps times our seconds. They give us an hour, we have to put it in seconds. So we take our 10 amps, times it by 1 hour, which is 3,600 seconds, and you get 3.6 times 10 to the fourth coulombs. Okay, now we know that those 3.6 times 10 to the fourth coulombs. We know that 1 mole of electrons has a charge of 96,500 coulombs. So we can take our coulombs and convert them to moles of electrons using this equation right here. So using that, now we've got 0.373 moles of electrons. Okay. In this equation, when Al3 plus becomes Al, we know that there are 3 electrons that are gained. So that's the number of electrons that are transferred. So for every 1 mole of aluminum that is produced, there are 3 moles of electrons that are added, that are gained by that substance. So then we get our moles of aluminum, and then we simply go from moles of aluminum to grams using the molar mass of aluminum. So you would get 3.36 grams of Al. Okay, here it all is in one step. You certainly don't have to separate out how I did. I just wanted to show you each step individually. But you take your amps times seconds to get this number. You go from coulombs to moles of electrons to moles, and then moles to grams. Okay, now what happens though is a lot of times when you have these aqueous solutions, water can also be electrolyzed, and so it causes it to be a little bit more confusing. Because water can be oxidized to form O2, or it can also be reduced to form H2. So the way that you determine which of the two processes will occur, will the substance be oxidized or reduced, or will the water, you have to use the standard reduction potentials. Okay, for the reduction process, the reduction potential that has the less negative value will be the one that is reduced. Okay, for oxidation, the half reaction with the more negative value for the reduction potential is the one that will actually be oxidized. Okay, and we'll look at that. Well, some of these problems deal with that. We'll look at that tomorrow in class. There's a whole bunch of problems we have to do. This might take us a couple of days to do all of them. Start looking at those though, and when we'll look at these, this water one kind of throws things off a little bit. So we'll look at that tomorrow in class. Okay, it's easier just to look at problems than sit around here and talk about it. Okay, if you have any questions, please write them down, and we'll talk about this tomorrow in class.